Hi guys, so in this video we're going to take a look at derivatives and their applications to motion. For simplicity, we'll be considering motion in a single dimension only, so motion of a particle along a straight line and back again. As part of this video today, we'll be looking at vector and scalar quantities and describing what those mean, and we'll be looking particularly at distance and displacement, speed and velocity, and acceleration. To start with, we need to explore the difference between a scalar and a vector quantity. A scalar quantity is a quantity or measurement that has magnitude or size only, whereas a vector is a quantity or measurement that has both a magnitude and a direction attached. One example of the difference between a scalar and vector comes in measuring either distances or displacements. A distance can be stated as, for example, 5 meters, whereas a displacement is always stated with a direction, so 5 meters north, which would be different to moving 5 meters south or 5 meters east. In the same way, a speed, such as 60 kilometers per hour, is a scalar quantity, whereas a velocity, such as 60 kilometers per hour northwest, is a vector. When dealing with accelerations, though, there is only the one term for both scalar and vector quantities. Accelerations can be stated, as in the case of 3 meters per second squared, without a direction, or in the case of the acceleration due to gravity, 9.8 meters per second squared down. At this point, it's important to note that the notation for speeds and accelerations can be written in two different ways. We can have it written as either meters per second or meters second to the power of -1, and meters per second squared can be written as meters second to the power of -2. What we've got here, guys, is a graph of the motion of a particle in a straight line. And we need to unpack the features of this graph in order to understand how the position and velocity of a particle are connected by derivatives. So looking at this, we can see that the particle initially began at time t at a position of 0. So at the start, it's here. It then moves so that some time later, so at t1, it has moved a distance of d. So if we consider this to be the positive direction, then the particle has moved from here out to some distance d. It then stops because for the next several seconds, minutes, however long this is until t2, its distance does not change. Then, after this point, it returns to the initial point, x equals 0. But it does so over a much greater time period. So that means as it comes back, it does so much more slowly. It takes a longer time to cover the same distance. And that gives us the connection between displacement and velocity. When velocity is faster, the slope of this displacement graph will be large. Whereas when the particle is moving slower with a lower velocity, the slope is smaller. Also, when the particle was moving forwards, the slope was positive. Whereas when the particle was moving backwards, we had a negative slope. To summarize this, we've interpreted a large positive slope to mean fast forward motion, and a smaller negative slope means slow backwards motion. We can also see here that we had a 0 slope, and we have interpreted this 0 slope as being no motion, the particle being stopped for that time period. Now the slope of a function is just given by the derivative, and we can see from this that the derivative, d dt, of a function of position with respect to time is just going to give us a velocity function. In other words, we get the velocity of a particle at any point if we know how the position is changing at that point. And that makes sense, because velocity is just how quickly the position is changing. We can do exactly the same analysis if we look at the velocity graph of a particle. We can see here that we had a particle that at time 0 had an initial velocity vi. The particle then accelerated, got faster until it was moving at a velocity of vf. It then, at this point t1, stopped accelerating and stayed at a constant speed until this time t2, at which point it rapidly decelerated. It accelerated in the negative direction, so its speed slowed down until it stopped. Its velocity was 0. So it's very easy to see that our derivative of velocity with respect to time, so d dt of our velocity function, is just going to give us an acceleration function. The slope of the velocity, how quickly the velocity is changing, is the acceleration. In the last section, the particle was slowing down. The acceleration was in the negative direction, which was causing the speed of the particle to decrease. But what happens if that continues even after the particle has stopped? Acceleration in the negative direction would then cause the particle to speed back up, but in the negative direction. So the particle would start moving backwards, getting faster and faster. So it's important to realize that acceleration is directional as well. Acceleration in the negative direction, if the particle is moving forwards, will cause it to slow down. However, the particle will then stop and start moving backwards, and the acceleration in the backwards direction will then continue to speed the particle up. On the graph, though, this negative acceleration always is seen as a negative slope. The slope just simply continues through 0 into the negative velocities. So what we've seen now is that the slope of a velocity graph, of a velocity function, is simply the acceleration. So the derivative d dt of the velocity function vt gives us an acceleration function. The acceleration at any point is just given by the rate of change of the velocity. So to summarize, a larger slope means a greater acceleration. A positive slope means accelerating in the forward direction. A negative slope means accelerating in the backwards direction. And a zero slope means that we've got no acceleration at all, which is the same as saying we have constant velocity.